Okay, so welcome to first lecture on group theory. So let us begin with some examples. So first example is that you look at the set of all integers 0, plus minus 1, plus minus 2, plus minus 3, and so on. This is the set of all integers. Okay. Now we have usual addition operation of integers. The usual addition operation on Z uh, satisfy the following properties. The first property is that if m and k are any integers, then if I take m plus n and then add it with k, that is same as if I take n plus k and then add it with m, right? So this property is called the associativity of that addition operation. So this associativity operation allow you to perform the same operation in a multiple times without uh, ensuring that whatever way you do this operation, perform this operation, the end result will be the same. Like you first add n with m and then add k with it. That is the same as you add n plus k with m, right? The second property the usual addition have is that there is a special element, namely the zero element, which has the property that m plus 0 equal to m, and this is equal to 0 plus m for all m belongs to set, right? You take any integer, add it with 0 in whatever direction, you get the same number m, right? This is called the, so therefore the 0 acts like a neutral element with respect to addition, right? So this element is called the neutral element for addition or the identity element for addition. Okay. The third thing is that uh, given any integer m, there is a negative integer minus m that exists. Another integer minus m belongs to z, such that m plus minus m is the relative identity is equal to minus m plus n, right? So therefore, every element, every integer admits is inverse with respect to addition operation. Okay. So now look at another example. So you look at the set of all real numbers, set of all rational numbers with respect to addition, set of all real numbers with respect to addition, the set of all complex numbers with respect to addition. All of them have the similar kind of properties. The addition is associative. Addition is there is a zero element which acts like a neutral element for addition. Every element admits its additive inverse in these examples also, right? Let's see another non-trivial example. Let's consider R star means R minus 0. Set of all non-zero real numbers. Now, note that we have a multiplication of two non-zero real numbers is again a non-zero real numbers, right? So the multiplication defines an operation, binary operation from R cross on R cross, given by you have two non-zero real numbers, send it to A times B product, right? So this has the same other kind of property. That means the multiplication is associative, right? A times BC is equal to AB times C for all A, B, C in R star. Second property is that there exists one in R star, such that satisfying the property that uh, A times 1 equal to 1 times A equal to A for all A in R star, right? And the third one is that given any A, so A being a non-zero real number, it inverse exists. So there exists a real number called 1 by A in R star, such that A times 1 by A equal to 1 by A times A equal to 1. Multiplicative identity. Okay. Let's see another such example. It's a non-trivial example. So you take fourth example. You take the set of all say matrices. Okay. Set of all matrices m by n matrices who are real. The set of all m by n matrices with real entries. Okay. Now we know that given two such matrices A and B belongs to m by n over R. So their addition m A plus B, sorry, A plus B. This is also another m by n matrix over R, right? So the usual addition of matrix upper matrix addition, this defines a binary operation on this set. This set with this addition operation also have the same property. Namely, addition is associative. A plus B plus C equal to A plus B plus C for all A, B, C in M. This the second property is that there is a zero matrix, means all entries are zero, such that A plus 0 equal to 0 matrix plus A equal to A for all A in M. Okay. The third property is that given a matrix R, there is a matrix B which is nothing but minus of the matrix A, means that replace all the entries by minus A. So this is basically minus Aij. If A is the ijth entry of A is Aij, and minus Ij minus Aij is the ijth entry of the matrix B. Says that A plus B equal to 0 equal to B plus A. Okay. So see that all these in this all examples, we have these three properties are common. Okay. So we can take this three property as a model to define something a mathematical system which is called a group. Definition. A group is a pair G comma star where G is a non-empty set and star is a binary operation on the set G satisfying the following properties. The first property is that the binary operation should be associative, meaning that A star B star C equal to A star B star C for A, B, C in G. Second property is existence of neutral element. So let me just say that this property is called associativity property. The binary of a star is okay. The second property is that existence of identity or neutral element. That exists E belongs to G, the special element says that given any element A, you have E times E equal to E times A equal to A for all A in G. That is existence of inverse. Given any A in G, there exists P belongs to G such that A times B equal to identity equal to B times A. Okay, in this case, B is called inverse of A and it is denoted by A inverse. Okay, it's clear. So all the three examples we have seen before, just a few minutes ago. So they are all examples of a group, right? So let's see a few more examples. Okay, so consider the S1, the unit circle Z in C such that mod Z equal to 1. This is the unit circle inside the complex plane, right? So note that with respect to multiplication operation, this forms a group because if you have two complex numbers Z1, Z2 from S1, then mod of Z1, Z2, this is equal to mod Z1 times mod Z2, but Z1, Z2 taken from S1, so therefore their modulus are 1, so this is equal to 1, right? So Z1 times Z2 is in S1 also. So the multiplication is a binary operation on SP, right? Now clearly this operation is associative, namely Z1 times Z2, Z3. This is equal to Z1, Z2 times Z3, right? Or Z1, Z2, Z3 in this one. Second is uh, there is a special one element 1 in S1 which satisfy the property that Z times 1 equal to 1 times Z equal to Z or Z in S1. That property is that given Z belongs to S1, so there is 1 by Z. So since mod Z is 1, so 1 by Z exists. Means Z is non-zero in particular, so 1 by Z exists, and it also has modulus 1. So 1 by Z belongs to S1, satisfies so that Z times 1 by Z. We know that this is equal to 1, equal to 1 by Z times Z. Right. So therefore, S1, this unit cycle in a complex plane, is forms a group with respect to multiplication operation. We call it a cycle group. Okay. Well, let's see another example. Say you take um, say Q square root of 2 in the set of all A plus B square root of 2 such that A, B belongs to rational numbers. Right. So this is a subset of R, right? Show that Q square root of 2 is a group with respect to addition of real numbers. Very elementary. Okay. Now we see a very nice example. It's a very useful yet non-trivial example of a group, which is given by the congruence class of integers modulo n. So let me define it formally. So take x an integer and get a number 2 and and let us define a relation uh, which is denoted by this on Z by setting A congruent to B mod n if A minus B equal to nk for some integer k. Okay. Well, now note that A is congruent to A for all A belongs to Z. Right, because A minus A is 0, which is divisible by n. So this is reflexive. So it's a reflexive relation. So if A is congruent to B mod n, and uh, then A minus B equal to nk for some k belongs to Z, This gives B minus A. This means that B minus A equal to n times minus K. This implies that P is congruent to A mod n. So yes, the solution is symmetric. Now note that if A is congruent to B mod n and B is congruent to C mod n, then A minus B equal to nk and B minus C equal to nl or some kl close to integers, then A minus C is equal to A minus B plus B minus C is equal to n times k minus l. So A is congruent to C mod n. Therefore, this congruent modulo n, this relation is transitive. Since this is reflexive, symmetric, and transitive, so therefore this is an equivalence relation on set. So once we have an equivalence relation on a set, that set breaks into disjoint union of its equivalence classes. Right? Let's see how equivalence class of an element looks like. Now, for A belongs to Z, it's this equivalence class is the subset consist of all integers B belongs to Z such that B is congruent to A mod n. So that means B minus A is divisible by n. So this is nothing but that P belongs to Z such that B equal to A plus nk or some k z, right? So therefore we can rewrite these elements like A plus nk such that k belongs to z, right? So therefore this class is nothing but of this form A plus nz of this form, right? Okay. Now, now note that Z is a union of the equivalence classes, and two such equivalence classes A and B given any two elements A, B in Z, either their classes are equal or they are completely disjoint. This is a very basic property of equivalence relation, equivalence class. Sorry, this is the empty set. Right? Now let Zn be the set of all such equivalence classes. So now note that given any a, given any integer a belongs to z by division algorithm, there exist unique integers b are in z such that a equal to bn plus r, where either r equal to 0 or r is strictly less than or 1 less than equal to r less than equal to n minus 1, right? So therefore now from this lesson we see that therefore uh, the class of that integer, so therefore a minus r is equal to bn, right? So therefore the class of a and class of r is means a and r are related modulo n. So therefore their classes are set, right? Now the choice of r can be from 0 to n minus 1, right? So therefore there are exactly n many elements in Zn, and they can be represented by class of 0, class of 1 up to class of n minus 1, right? Now we can define the addition operation on Zn as follows. Define addition modulo n operation on Zn as follows. You would set the class of A plus class of B, define it to be class of A plus B for all class of A, class of B, and Z. Now, the little thing you have to be careful about is that uh, an element in Z may be represented by two distinct integers, right? So you have to show that this operation is well defined. Now check for well defined. Suppose that class of A equal to class of A prime and class of B equal to class of B prime or some A prime B prime in Z. Then we have to show that the class of A plus B is actually class of A prime plus B prime. Otherwise, see, this addition operation defined in this way may not be well defined. So for the sake of well definedness, so you have to show this relation, right? This equality. Now, how do you show this equality? So we have given this information that class of A equal to class of A prime. So from this you get that A minus A prime equal to nk, and from this you get that B minus B prime is equal to nl or some kl in Z, right? When A plus B minus A prime plus B prime, which is A minus A prime plus B minus B prime is equal to Nk plus L into A plus L. So the class of A plus A prime equal to class of B plus B prime. Sorry, class of A plus B equal to class of A prime plus B prime. So therefore, the addition operation on Zn is well defined. Okay. Now note that with respect to this addition operation, this set Zn forms a group in it. So this A plus B plus C, this is equal to A plus B plus C equal to A plus B plus C equal to, now within this bracket we have the usual addition of integers, so which is associative. So therefore I can rewrite it as B plus C. So then we get this, right? So this happens for all A, B, C belongs to Zn, right? So therefore the addition modulo n operation on Zn is actually well defined. Now existence of identity. So look at the class of 0. Class of 0 in Zn has a property that you add any class with it, you get 0 plus A is equal to K. Similarly, A plus 0 is equal to this equal to A, right? So the class of 0 is the additive identity in Zn. Now next note that if you have any A given the class of A in Zn, take class of B to be class of minus A in Zn, then class of A plus class of B is nothing but class of 0 and class of B plus class of A, because I have taken B to be minus A. So therefore every element admits its additive inverse inside Zn. So therefore Zn plus this setup is satisfy all the axioms of group. This is a group. Yeah. Okay.